Okay, welcome. This is the first lecture. We're going to talk about, I'm going to start with linear algebra, and I'm going to mostly talk about matrices in this video. So, without further ado, let me start. So, what is linear algebra? Basically, it's the study of vector spaces that are linear, and we deal with how to manipulate the linear spaces and the linear functions that are there within. So you could think of it's essentially a study of flat planes, flat functions, basically straight, they're just straight. The opposite is nonlinear algebra, which is functional analysis, where we deal with nonlinear functions and nonlinear spaces. Functional analysis is usually a bit complicated and it's usually studied after real analysis. Linear algebra is useful in our world and it's used in imaging, robotics, machine learning, and large language models like ChatGPT. Basically, to do anything in mathematics, essentially it's almost anything, you need linear algebra. Like, not necessarily a solid understanding of linear algebra, but a proper understanding of linear algebra to some extent. In this video, we're going to cover, in this series of videos, we're going to cover matrices and operations. We're going to look at vector spaces, linear transformations, determinants, and elementary canonical forms. There are much more, there are other things like, what are they called? We could look at normalization and all that. But I'm not really going to look at that. I just want the basic understanding so that I may be able to go into real analysis. The reference book is going to be Kenneth Hoffman, Linear Algebra. And I'll also use basic linear algebra from Springer. I forgot who the author is. Linear algebra by Kenneth Hoffman is quite complicated and I had to self-study. And I'm an electrical engineer, I'm not a mathematician per se, but I want to get into pure mathematics, so I started with this. But this thing is tough. If you don't have prior knowledge of linear algebra, don't start with this one. So what's a matrix? A matrix is a squarish combination of items that can be used to perform magic tricks. And what do I mean by magic tricks? If you look at how extensively matrices are used in the mathematical and electrical fields, you'd be surprised. Yeah, matrices are used a lot in finance, in electrical engineering, in pure mathematics, in quantum mechanics. It's everywhere. Matrices are everywhere. Like, you could think of something like Heisenberg came up with a certain form of matrices that's used in quantum mechanics, which had some dispute. He had some dispute with Schrödinger. Yeah, something like that. I'm not really sure about that, but what I know is matrices are used everywhere. I can tell you my field, electrical engineering, yeah, we use matrices a lot, especially analyzing nodes, electrical nodes, yeah, in electrical networks. A matrix looks like this. As you can see, the red at the top, the red numbering 1, 2 to n, those are the columns. 1, 2, 3, the green ones to m, those are the rows. So the elements are A11, A12, and there we insert the specific numbering or the specific items that we want to manipulate. A matrix has rows and columns, and it looks like that. We can represent an n by n matrix in the form as given below, with x1, 1, 2. It's almost the same as the previous one, right? Yeah. An m by n matrix with essentially m times n elements. Okay, because you can see that each column will have m elements and each row will have n elements, and in total it will be m times n. Here are examples of matrices. The first one is a 1 times 5, meaning it only has one row and 5 columns, and you can see the columns are 10, 9, 8, 7, 6, but it only has that single row. A 3 by 2 has, as can be seen on the top right, you can see that the rows are 1, 2, 3, 4, 5, 6, but the columns contain 1, 3, 5, 2, 4, 6. The others are square. The 4 by 4 is we call it a square matrix, and as you can see, it has 4 rows and 4 columns, and the other one is a 3 by 1. In matrices, we have different operations that we can perform. We can perform addition, we can perform multiplication, we can perform something called a cross product, but that's a bit too advanced for now. Let's look at addition. Addition is done element by element. So if we have like matrix A with 4 elements and the matrix B with 4 elements, we start with the top left for each. Then we add like A11 plus B11, A12 plus B12, A21 plus B21, and finally A22 plus B22 to form a new matrix. The same can be done generally for larger and larger matrices. It is done positionally. I've forgotten the name that I'm supposed to use there. Matrix subtraction also follows from addition. It's also done in the same way, but we just subtract. And one thing that has to be noted is that addition is commutative, meaning that A plus B is equals B plus A. And in notational form, to reduce the complexity of representing it as this, we use I and J, and you can see A, I, J plus B, I, J. That means that if you have matrix A and B, we add like A11 plus B11, A12 plus B12. You see I and J, they must correspond. From now on will depend on the condensed form, yeah. So this is how we'll be representing matrix elements or matrix operations. Yeah, matrices are represented like this. Like as you can see there, X is basically the specific element where at row I, column J of an M by N matrix. This is how we represent we represent a matrix itself. The matrix itself is represented like this. This is the condensed form. Matrix properties, it has other properties. The first one is distributivity. It means that if we multiply a scalar to the addition of two matrices, we just distribute it. It's distributive. If we add two scalars and multiply it by a matrix, it's the same as distributing the matrix to both scalars. The other one is basically associative. The other one is multiplication by a negative, and the last one is if we multiply a matrix by 0, it doesn't matter. Yeah, basically a 0. I could say a matrix 0 or just a field 0. You will get the 0 matrix. We'll talk about fields later on. Matrix multiplication is done as follows. Suppose we have matrix A and matrix B, and we want to form matrix C by multiplying A and B. We have to take the first row of A and multiply like as you can see, A11 times B1, A1 times B1, A2 times B2, and A3, A1 times B1, A2 times B4, A3 times B7. Then we add the 3 to form C1. I can't really find one that will explain it properly, but essentially it's usually performed like row 1 of the first matrix and column 1 of the second matrix to form the first element, then the first row of the first matrix and the second column of the second matrix to form C2, and so forth and so forth. And matrix products can be represented as follows: A, B, I, J is equals to that. For example, suppose this is A and this is B. As you can see, we take the first row of A, which is 0, 1, 0, and the first column of B, which is 2, 1, 1, to form the first element of AB, the top left. So as you can see, 0 times 2 is added to 1 times 1, and then it's added to 0 times 1 to form the top left of matrix AB, which is 1, and so forth and so forth. This is elementary. And we also have to note that matrix multiplication is not commutative. Yeah, it is an uncommutative ring. Wing. Okay, what's a field? A field is a set with elements such that for x, y, z, and lambda in the field, addition and multiplication properties hold. Basically, fields, consider something like the real number line. That is a field because of some property. Let's look at the properties first. Addition properties, which number one is commutative. So if I take x plus y is equals to y plus x, example, 1 plus 2 is the same as 2 plus 1. Associative, 1 plus x plus into brackets y plus z is equals to x plus y, z. That's associative. They also have an additive identity and additive inverse. Okay, additive identity is 0. Basically, 0 must exist in the field. In the field, for each element in the field, there must be a number such that if you add the two of them, it will give you 0. Multiplicative properties include distributive, in which if I multiply outside the brackets, I can distribute it inside. Inverse, which is called the multiplicative inverse. Each field has to have an element such that if for every element there is an element, if I multiply the two of them to give me 1. Commutativity, meaning that if I multiply two of them, they can migrate. Associative, meaning that I can distribute the brackets wherever I want. And also a multiplicative identity, 1 must exist in each field. Systems of linear equations, these are essentially, consider linear equations, okay, of the form like ax is equals to b. Okay, that's called a linear equation. Now, if we have multiple variables, it will be of the form like a1 x1 plus a2 x2 plus a3 x3 blah 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 is equals to b specific. Now, if you have such a system, we can represent it in matrix form. Like, consider the one given here. You can see that the equations given below are 2x minus y is equals to 0 and negative x plus 2y is equals to 3. Now, we could take, since x and y is common to both equations, we can represent it in terms of a matrix, and 2, negative 1, and 2 can be represented as A, and the right side can be represented as 0, 3. Basically, it follows from matrix multiplication, which we've talked about previously. Okay, equivalent systems. If two systems of equations have the same solutions, we call them equivalent. So if ax is equals to y and cx is equals to z have the same solutions, we call them equivalent systems. And that also means that one of these systems can be represented as a sum of as a linear combination of the other one. Like, for example, consider ax is equals to y. It looks like this: a11 x1 blah blah blah. It goes like that. If we take all these systems of equations and say, like, the first row, which is a11 x1 a12 x2, if we take that one, we multiply it by c1 and go on to each and every row and multiply c1, c2, c3. You see, so row 1 multiplied by c1, row 2 multiplied by c2, so on to row m multiplied by cm. If we take all that and then we add them together, it will essentially give us bx is equals to z, of which b11, you see the term that has c1 a11 blah 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 to cm a m1 x1, that's essentially b11 x1. Okay, no, that's basically column 1. Yeah, column 1 of b, as can be seen. And an example of two systems that have the same solutions are the ones that are given below: x1 minus x2 is equal to 0, 2x1 plus x2 is equal to 0, 3x1 plus x2 is equal to 0, and x1 plus x2 is equal to 0. And you can verify that they have the same solution, so we call them equivalent. And you can try to represent one one in terms of the other. Okay. Now, matrices. In matrices, we could perform elementary row operations to aid in something called Gaussian elimination, which we'll talk about later. And what do we mean by elementary row operations? Elementary row operations are operations that are performed on rows to make them appear in a simpler manner. And in simpler manner, we'll talk about that later on. So, and what are the elementary row operations? 1, scalar multiplication. Number 2, addition of 2 rows. And number 3, swapping rows. We say that 2 matrices are row equivalent if you can reduce one matrix to form the other by the means of row operations. So essentially, A can be reduced to B using the row operations, which are scalar multiplication, addition, and swapping. Gaussian elimination is used to reduce matrix problems to simpler, more solvable ones, because matrices can grow exponentially and it will be very difficult to deal with them, especially in something like large language models. So to deal with matrices, we need to reduce them into row echelon form. And what do I mean by row echelon form? It's a simpler form basically that can be used to find the solutions much more quicker, because you can see like the top left is 0, 0, 2, 1, negative 1, 1, negative 1, 1, negative 4, and that's much more complicated to solve. I can't really say it's much more complicated to solve. Yeah, it's a bad example, but essentially you can see we've reduced the last row. We wanted to have 0, 0 something. Okay. Elementary matrices. An m by n matrix is said to be elementary if it can be obtained from the m by m identity matrix by means of a single elementary row operation. And what is an identity matrix? Is the one that's given at the bottom left, which is M. You can see that all the diagonal elements are 1 and all other elements other than the diagonal are 0. We can represent it using the Kronecker delta 1, 0. The rank of a matrix is the number of independent rows or columns. So, and what do we mean by independent? If I take the sum of all the rows with